Well, it's of course a great pleasure for me to be here to this celebration of great achievement of my friend Yakir. And I must say I was always extraordinarily impressed by the way he could take some crazy type of quantum paradox and then solve it.
Can you speak over here?
Okay. And solve it, that I could not resist also to present the paradox and hopefully give some indication of its solution based on one of his great achievements, at least I think it's one of the great achievements of the theory of weak values. So the paradox in question is the well-known black hole paradox. As you know, probably, the paradox comes from an alternative. See, either the black hole, the Hawking radiation of the black hole doesn't contain any information, in which case unitarity would be lost and therefore quantum mechanics, except I pass over some quite of even more difficult solution, except if there would be some remnant which would probably be infinitely degenerate. Now I think that solution I have, after having some sympathy for it, I think I don't like it, essentially because it's very difficult to reconcile with, after all, some of the positive results obtained in string theory and ADS-CFT. So the other alternative is that everything is contained in the Hawking radiation. In other words, it contains the information, but then, of course, one is led to the idea that probably something is deeply wrong in the Hawking derivation, which also, I think, is something very difficult for me to accept, because it's it has a lot of consistency. I will talk about it a little bit, and I have hard to believe it's wrong. So this is essentially another alternative which has to do with, let's say, the complementarity scheme which have been done before. And the idea comes from the following. Namely, I will show that the detailed response of gravity to quantum matter is determined by the weak value of the energy momentum tensor. And that seems to lead to the fact that a horizon cannot survive this quantum mechanically, and therefore that if there's no horizon, if the space-time is somehow trivial, then there's no reason why the S matrix should not be unitary. However, the free-falling observer, as we shall see, will not see that terrible effect of getting out of the horizon. He will recover the horizon, and therefore the Hawking radiation will be, for him, the right thing to expect. And these are not contradictory, as I think I will try to show. Namely, it's a quantum complementarity in which the free-falling observer, the proper history of the free-falling observer is not contradictory with the unitary reconstruction of its fate. And now, although the unitary amplitude cannot be done without cannot be computed without a theory of quantum gravity, I think the complementary scheme, which I'm going to present, is independent of it. So, what I will do is first to recall for everybody what the Hawking radiation and how the information paradox comes of it. Then I will briefly review what is the weak values operator in quantum mechanics and how it can lead to the back reaction to a problem, and then discuss the problem of how the S matrix can be achieved with a horizon which comes and goes, as we shall see. So, if you have an incipient black hole, essentially is a conventional thing where you have here the horizon and a collapsing shell or a collapsing star. You have a time-dependent process, so you have pair creation. And because you are getting close to a structure which is called a horizon, the system becomes universal. And taking the trace on the horizon, you find that you have a thermal density on light-like infinity, which is chi plus, with a temperature which has no information at all except the value of the mass. Now, I want to insist before starting on a few very simple points. That the Hawking radiation doesn't have anything to do with what happened outside the horizon. Inside the horizon. It arises solely from the region outside the horizon, or at least can be derived that way. And that the process is obviously unitary at that stage, where I have not included back reaction between the initial Cauchy surface being chi minus and the final one, which is the tensor product of H and chi plus. And the radiation clearly doesn't contain any information except the mass of the black hole. Now, is there a problem with the horizon? Well, the first thing that you can see is that there is something that might be a problem, which is the Transplanckian issue, because the Hawking radiation starts very close to the horizon, deep inside, where the creation happens. So I use the advanced coordinate, which labels chi plus, and the retarded coordinate, which labels chi plus, and the advanced coordinate V, which labels chi minus, and the tortoise coordinate, which is confined to the region outside the horizon only, which is what I want to do. So then the Schwarzschild metric takes the following form, and the Hawking radiation starts essentially when the factor, or the G00 factor 1 from M, can be written as the exponential of the retarded time, which is here. That is when it starts, and Vs is the value of the advanced time when the star crosses the horizon, and this happens at a time, let's say, where the shell is at a distance of order m of the Schwarzschild radius. I'm using absolute units here, it's always the Planck size. So, well, a very short time after time of order m, that's the time of emission of one photon, essentially, the frequency becomes very large, and after the frequency of the Hawking ancestor, let's say, when you are close to the horizon, is essentially, you can approximate it by the value of the temperature, the local temperature, so temperature divided by square root of G00, and that is given by that exponential, or in terms of the initial time, by this expression. And because the lifetime of the black hole is of order m cubed, that means that the local frequency that you're facing is of the order, dropping all the power laws, of the exponential of the square of the mass of the black hole up to a numerical constant. So that seems an enormous effect as far as the vacuum fluctuation are concerned, and the question arises, to me, that is the horizon stable against these Transplanckian fluctuations? Well, at first sight, it would seem it is, that there is no problem with that, because if you compute the average energy momentum tensor, which you would think is the thing that drives the back reaction, you will see immediately what happens. Let me make a simple computation so I can do things mathematically, but it's not really necessary. Let me suppose I have only S wave, I drop the relativistic barrier, so I have a two-dimensional model there. And in fact, for further computation, I will even use a light-like shell, which also simplifies without changing very much of the problem. Now, because now, if I do that approximation, we are essentially in a two-dimensional model, and then I can compute the UV value, expectation value of the energy momentum tensor by the trace anomaly. R here is a scalar curvature, and you get that expression. Out of this, you can compute the other component of the energy momentum tensor up to a integration function, a function of v for TVV and a function of u to TUU. And that, for TVV, clearly that function has to be 0, because when r goes to infinity on sky minus, we are in Minkowski space and nothing should be there, so this has to go to 0. Now, for TUU, that's different, because there we have the Hawking radiation, which is going to contribute. So, everything now will depend on the value of TU. If TU is equal to 0, there's no collapse. We are in what we call the Boulware vacuum. That is essentially what you would get if you would fix a star on the horizon. Obviously, that gives a singularity. And so this is, but if you have a Hawking radiation, then you can compute, in this case, which I have seen here, and you have a number which is just the value of the thermal radiation, which is 1 over 48 pi times 1 over 4m squared. Why did I put that number in? Well, because now we can look what happens when we go on the horizon. TVV goes to a constant, which is there. TUV goes like a simple 0, and TUU goes like a double 0 when you go to the horizon as a consequence of the Hawking radiation. And this now has a significance, which actually is more general than this computation, that if I look at a geodesic object falling into the black hole, then when r goes to 2m, the u velocity goes like a simple pole, and the v velocity goes to a constant. Therefore, this is exactly what one needs to compensate for the scalar TU mu, u mu u nu, to be regular on the horizon. So we see that T mu nu is totally insensitive to the Transplanckian fluctuation, and you would seem that the Hawking radiation appears to ensure consistency of the global geometry. And so the Transplanckian object seems to be completely irrelevant. However, then you're led into another problem, because if you don't care about what happens on the horizon, then you see that if you include a back reaction, you should expect a Penrose diagram of that type, because the horizon first goes to 2m when you 0 to 2m when you go to the surface of the star, and then with the evaporation of the star goes back to T0 where you join the singularity, and then thing gets to Minkowski space. Clearly, if that has no horizon, no information on Sky Plus, and if there is a singularity in which everything disappears and r equals 0, you lose all correlation and unitarity will be lost. So we do not want that, because somehow we want to keep quantum mechanics, never doesn't mind the way it will be realized. Will it be field theory? Will it be string theory? ADS-CFT? We anyway want to keep unitarity, so is really information lost in the singularity? So we are confronted with a problem. How can we try to restore unitarity? We can try to restore it either on the singularity, maybe, or we have to re-examine the problem of the horizon. This is what I'm going to do, and I'm going to discuss the possibility that the horizon effect is what is responsible to restoring the unitarity, because it will lead to a dependence of the geometry on the outstate when we will do things a little bit more carefully than just taking the expectation value of the energy momentum tensor. For that, I need to review in a word what is the operator weak value. In general, in quantum mechanics, one just specifies the in-state and then let it evolve. But one can gain some more detailed information on the system by fixing also the final state, and then the weak value of an operator is defined by the switching A between the initial and the final state, and divided by the amplitude of finding the initial state in the final state. Now, and this is the Heisenberg way of writing it, which is slightly more concise and which I will use. Now, I'm not going to go into all the beautiful results which have been obtained with the weak value, because it will come from us in the problem which I am studying. So, how is unitarity expressed in this form? Well, you see that the expectation value generally of an operator is written as a sum of eigenvalues times the probability to find the eigenstate in the initial state, but we can also express it in terms of the weak values by summing over all the final state with probability, which is the probability of finding the final state to the initial state. Just multiply here denominator and numerator by Fi, and multiply by the probability, which is the denominator, and sum over F, that's the unitarity. So this is another way to compute the expectation value from a more detailed structure, which is the weak value. Why am I interested in that? As I said, the detail that we wanted to do is that we want to see if sticking to the outside of the horizon, we find that we don't get into an inconsistency when we get to the horizon. So if I now compute quite generally the amplitude of finding a system initial state A, final state B with matter and gravity, I have at least formally whatever G mu nu means. It could be some underlying theory, whatever, but I write formally the following expression in terms of the action, which is the path integral expression. Now, let's suppose that we are in the neighborhood of some background, like we have in the black hole in absence of back reaction. Then this amplitude, this is given as here by fixing two hypersurface, spatial hypersurface, sigma 1 and sigma b. Here they are fixed in the background, which we don't know what it is, but we have a function integral, and in order to cope with the background, we shall split the fields phi into classical fields, some classical fields, or which, let's say, are responsible for collapsing of the star, and a genuine contribution to gravity, where Sg is the value of the action, where the quantum field phi, the only one which we left, goes to 0. And then we develop this action in terms of the fluctuation around the initial value. This is the general expression here. And so we first factorize the term independent of the vacuum fluctuation of the gravitational field, and then expand that part, which depends on the quantum field, to first order in h mu nu, which can also be written in this way as an exponential in terms of this plus additional terms, which are at least second order. Now, what 3? No, that's not true. I was 20 minutes here. Well, I have only 10 more minutes, so. And okay, so the question is whether we can use steepest descent. Now, if we could use steepest descent to have a classical motion, then the value of BA is given by this, C is some determinant, and the first term has to vanish. Therefore, we have we would have a classical equation of motion where the value of dsdg mu nu would be d mu nu 0 as a function of the classical fields, And an additional term comes here, which in the Heisenberg representation is like this, which is nothing else than the weak value. Now, is a steepest descent value, is a steepest descent valid or not? That's precisely what we have to study. But if it's not valid, then we have a problem also. So I take a pure final state. I'm not going to do the computation here. Pure final state on Sky Plus. The total, the initial state can be expressed in the power series, in a, let's say, in the Hilbert decomposition, and we take a complete normal set of states on Sky Plus, and the weak value, I equal to 0, is just the initial state which is there. The final state will be the side psi times its EPR conjugate, which is there. And then the T mu nu, quite generally, can be expanded in three forms, because there's not too much time left. I will not explain exactly, but just a final result. That quite generally, the weak value can be expressed in terms of a term here, which is regular on the horizon, and which is the expectation value, which we studied before. There is a term here, which is the amplitude not found in the vacuum in the out state, which, of course, and when you do the computation, you find that just is restoring the Boulware vacuum, because this is going to compensate for the Hawking radiation, because there are no photons at the end. So this will be singular, or the sum of these things will be singular on the horizon. The last one must necessarily be the Hawking radiation, because of the unitarity relation, which tells us that if you sum this times the probability, you find the expectation value. So when you sum over all possible psi state with the EPR conjugate, you will necessarily cancel that term. That can be shown in detail, but that's what happens. So that is what you get, and this is the Hawking radiation. Now, what has that as a consequence? Well, nearly all states psi, I'm not going to do the computation here, obviously, contribute to a radiation term, which is this, which then take the value of the Transplanckian energy into account, and therefore the metric itself will become Transplanckian. And in general, there will not be any possibility of having a classical horizon. Use fluctuation in the vicinity of horizon are unavoidable if a generic out state is selected. That means that choosing a generic pure state on Sky Plus appears inconsistent with the steeper descent geometry in the vicinity of its horizon where the Hawking radiation occurs. The classical horizon, that I interpret as saying that is a conjecture in a sense, that the classical horizon dissolves in strong quantum metric fluctuation along the horizon. Now, this was done in the context of the absence of back reaction, but if you see what happened when you have the back reaction, clearly the problem of the horizon is exactly the same. So you would think that this should happen always. So post-selecting pure states should lead, expect, to a trivial causal background, but with strong metric fluctuation, depending on the in and the out state, where the whole metric field, or whatever he places, plays a role. And that appears when we approach a would-be horizon. If this is the case, then we have no reason to not to believe that the S matrix testable by an external observer is unitary. However, what happens so the typical diagram that we expect is a diagram where we have essentially the blue region is a true geometry, and here we have a region which is essentially quantum fluctuation, where the horizon, or the would-be horizon, would go from 0 to 2m, and then back here, and that picture should be essentially TCP invariant, which would be the full unitary S matrix for the black hole. Now what happens to the horizon? to the classical horizon. Well, taking back the U value again and taking the Massart-Parentani generalization of it, what happens if you make a partially weak value on the final state? If you take only know that something happens on the subspace, it would be 3 minutes. I have to finish. If not, the whole thing makes no sense. So if I take a partial post-selection here, then I just put here a projection on the states which are not there, and then it's clear if I just take the post-selection on the final state, it's just the fact that I don't know where it will come to, then I have to take, then it's trivial to show that this expression goes to the expectation value, which is the sum of the probability of the weak values. Now, if outstate, therefore, could not be tested by the energy momentum tensor, the energy momentum, if the outstate cannot be tested, then the energy momentum tensor will average out all the Transplanckian fluctuation, and the event horizon is recovered in a geometry which essentially is a coarse-grained geometry, because it's average over all the detailed geometry that you would get with the weak values. And I'm coming to the end. So, this is, so for such observer, like the observer who falls in, which has no time to whatever is outside or is inside the horizon before he can make any post-selection of what happens outside, then for such an observer, this type of Penrose diagram gets converted into the type of initial one that you would have, and he will just see the geometry in which the Hawking radiation was essentially valid. That's the message. So the summary of this is that the S matrix testable by an external observer, if this is right, I'm not claiming that I have a general proof, but that's essentially independent of what is the final theory of quantum gravity. The S matrix testable by an external observer is unitary, but in its proper history, the free-falling observer crosses an event horizon in a coarse-grained geometry, and actually the entropy of the horizon, that is just what we don't know in the post-selection, is measure its ignorance of the outstate. Now, there are obviously questions, and this talk has been a little bit too fast, so despite the fact that I took a little bit more. Actually, I don't think so. You started late.
I define proper time here.
Well, as you know, that's not the whole story. I define unitarity here, so unitarity I have to finish. So the question is, this is remaining some of the things that happens for static black hole, which I don't know really how to consider in this framework, which is related to the first-Ball conjecture, which has been studied in, particularly now in the context of ADS-CFT. What that imposes for cosmology and geometry, if this picture is right, and particularly for the landscape anthropopy bullshit, I don't know. But we should try to see and test if this picture is correct. Thank you.